gave me a piece. Yeah. I don't know what it is. Yeah. Yeah. I can respect that.
Okay, today we sort of exhausted all the stuff with chapter 2. We're into chapter 3 in transient analysis. Now, a lot of this stuff is, all the stuff that was evident and all this we're going to apply it here too. So remember this, this course continually builds on previous material, previous things. So I want to make sure that I'm giving you the problems. I want to go through some of these transient problems because you'll see how all the stuff you're learning is being applied now to circuit analysis with transient phenomenology. And in chapter 3, the problems, 1 second. Let me put this up here and then I want to get to it. I want to make sure you understand this. Fundamentally, when we have an RC circuit, that's a resistor capacitor circuit, and I'll draw a little larger. What we're always looking for is the voltage across the capacitor. Everything else is you don't worry about. I mean, if they want a current through a resistor, or they want a voltage at a different resistor, you don't worry about that. And once you get the voltage across that capacitor, everything else stems from that, and you'll see this. You got me on this, class? The fundamental equation is the voltage across the capacitor. This is for RC first order transient problems. It will always be some K1 e to the minus t over tau plus K2. That is the equation that is we're gonna find out what those constants are, but that's it. This is not gonna be anything a second order transient. It's not gonna have time varying sources in the solution in terms of a voltage or current source that's included. This is the solution for the voltage across the capacitor where you have something like a battery, which basically a battery, and the switch either turns on or off at t equals 0. Do you follow me on this? And it has a lot of applications in the real world. So that's it. Now tau is really equal to R Thevenin across that capacitor after t equals 0 times C. And I want to say that this is the solution right here for t greater than 0. It's after the switch does its thing. And the best way to really see how this is done is with examples. I can talk to them blue in the face, but until you see this applied and how to go about it, you're going to use all your circuit analysis techniques to find these values. I've got to tell you a few other things. Based on, we've had physics, but some of you probably don't appreciate it fully. When you have a capacitor, there's no current through there if there's nothing changing with time. For instance, if you put a capacitor across a DC battery, like a car battery, and put it there for a while, you'd find that it draws no current. The capacitor is like a very good insulator, but initially when you put it on, it charges up, so the current goes real high for a very short time, until you get a charge across there, all right? Some of you know that the charge across that capacitor equal to C times V, where V would be the voltage across it. That's equal to the charge in coulombs. I don't worry about that. In physics, they do. We're engineers, we worry about really things like voltages and currents and power. So with this in mind, let me do some of the problems. And I gave you a bunch. I want to do some of these things. And I like to start simple and work up to complicated. And that's the way I always do it. And I think everybody does, if they're doing this right. So for this case, what I'm going to look at is going to be problem 323 in the book. But you'll see how these examples really exemplify what I'm trying to get at. For 323 in the book, it has a 12-volt source, or my book, I should say. And then it has a switch, like so. And then it has 6K here. And then it has 100 microfarads here. So the capacitor here is 100 microfarad. And then it has 3K here. And what they're asking is, they're asking for the current here. You don't worry about the current there, and this would always be the information we're concerned about would always be for t greater than 0. And here's what happens. It has a switch like so, and that at t equals 0, it does this. Actually, it shows, I think, this condition. T equals 0, it goes from this position to this position. Let me see how he draws that. Okay, he does it this way. He's saying at t equals 0, it will go from this position to this position here. Do y'all follow me in this class? So it'll change states. And you've seen this kind of schematic for a switch, haven't you? Electrical switch. Basically, it's a Frankenstein switch. And mechanically, something's moving, right, class? All right. Now, when you do this, let's take a look at t less than 0, because we need the voltage across the capacitor for t equals less than 0. The steps I told you, it doesn't matter the order. You find VC for t less than 0. VC for t goes to infinity. R Thevenin. And from there, you get tau. And then you solve that equation. But those are the steps. So for t less than 0, and I'll say less than 0, what that circuit looks like, that switch is shorted there, right? Now please pay attention to this. So what it looks like is this. Remember, the switch is in position 1, so it looks like a short circuit to the battery, doesn't it, class? Or to the voltage source. How many see this okay? With me? All right. Can you all see it in the far back? All right. So that's what this looks like for t less than 0. The switch at t equals 0 goes from this state to this state. Got me? So when you look at this here, now, here's the thing. A capacitor for t less than 0, there's nothing happening. Do y'all follow me on that? If there's nothing happening, the capacitor looks like an open circuit. This is not a time-varying voltage source. That's a constant. It's like a battery, right, class? So you can erase it if you want. And you can just say, well, it's an open circuit. It looks like plus to minus VC 0. Call that that. That's just the voltage you're looking for. Everybody with me?
Why'd you erase it?
So you can get a better mental image of what you really need to do. You literally can remove that capacitor and just find the voltage that would be there if it wasn't there. I'm trying to help you, class, all right? This is not a bad way. Now, when you look at that, what is the voltage across this? This is basic circuits, right? This is one of those things you do in a second. What is it? How? Anyone?
3 over 9.
You all see from here to here, it's the voltage across the 3K, isn't it? Everybody with me? Far back, can you see it? If I want this voltage, it's just voltage division. I got 2 resistors and a voltage source. So it would be 12 times 3 over 9, right? Or 12 divided by 3, or 4 volts. So VC for t less than 0 is 4 volts. Everybody agree with that? There's nothing tricky, but you have to make sure you're attentive. Even if you don't like it. Even if you hate this stuff, you gotta be attentive. Now, next, are there any questions about this part before I continue? Everybody got it? Straightforward, right? It looks like an open circuit, rip it out. Find out where the voltage is that would be across those 2 dangling points. Now we go for t greater than 0. For t greater than 0, the switch goes down to here, right? This is what it would look like for t greater than 0. Everybody with me? I'm going to redraw it over there. But what really happens? Well, for T, now I put the capacitor back in. And I have that 6K, and I'm doing it this way for a reason, so you can see this. And this would be the voltage I'm talking about, right? Everybody with me? I just literally changed the state of the switch, didn't I, class? I want you to look at this and make sure this sinks in. Are there any electrical sources there? Is there a voltage or current source there, class? None. There's no battery left in it. There's no current source. Therefore, the final voltage must decay to 0. Do you all follow me? If the charge can get off the capacitor, in this case it can, it must decay to 0. So now we know this voltage as t goes to infinity is 0. With me so far? How many understand this, right? I know it seems overly simple, and I'm not trying to bore you, but you have to see these. This has to be obvious. Really, I'm trying to tell you the truth. Now, next, I find R Thevenin, right? I've got 2 of the 3 things I really need, right? So how do you get the Thevenin equivalent resistance? Well, this is the way I'd suggest it first. Literally erase that, if it bothers you, and put 2 dangling leads. I want R Thevenin across there. Y'all with me? How many?
Why are we doing, so our load in this problem?
There is no load. There is no load. We're only after the voltage across the capacitor.
Okay.
No load. This is a transient problem.
So we're not.
It's not Thevenin's circuit. I mean, you could think of the load as the capacitor if you want, all right? You're right, I guess you could say it that way. I removed the load, so the load is the capacitor. That's I'll credit you with that. You're good way to think of it.
Well,
Okay.
I was confused when we're solving this problem, or we're solving for I.
No, we're
V,
solving
right?
for V. We're gonna get I secondary. We're solving for the voltage across the capacitor. And anything else we want, like that I will get after we do that, okay? That's the key. Focus on the voltage. Remember that always. Anything else comes after we get this. Now, look at this. What is R? I call it R Thevenin across there. Yeah, you could say it's the R Thevenin across the capacitor as if the capacitor was a load. And you're right on that. Now, when I remove this, what do you see here? Tell me about these 2 resistors. They are in?
Series.
Parallel. Between here and here? Come on, they're parallel. Look, take a red line from here. You doing this to spite me or something? Take a look. From here to here. Remember, anything between the 2 colors is in parallel. I want it between these 2 dangling points. People have a thing with topology. Oh, it looks like it's a series. It must be. Look at where they want the value from, between where that capacitor was. You all see this? How many see this now? That's in parallel, aren't they, class? If it helps, I can do this. Can't I put the 6K this way, class? Makes it a little more parallel? Yes, miss.
So when you're finding R Thevenin, is it always for when T is,
T greater than 0, yes. It's always after the transient takes place, or after the switch changes state. So when you look at that, you all see that those 2 are parallel. When I say R Thevenin across the capacitor, think of it as the load ripping it out, okay? You take the capacitor's load, you tear it out. What does it look like now, okay? Everybody see they're in parallel. All right, now, what is the value by looking, class? What is it?
2.
It's 2K, isn't it? 3 and 6 in parallel is 2K. So I have R Thevenin is 2K, and I'll put it right here. And that means what? Tau right here is equal to R Thevenin 2K times 100 microfarads is 100 times 10 to the minus 4, right? So that's 0.2 when you do the multiply, right? Or 2 times 10 to the minus 1. You agree with me, class? Take 100 microfarads times 2,000 ohms, or 10 to the minus 4 times 2 times 10 to the third. You have 2 times 10 to the minus 10 to the minus 1, or 0.2. Do you agree with me? Okay, so that's 0.2 seconds. Now, I've got tau. Now I solve this. Who remembers what I said about K2? What is that value? Well, just look at the equation. What happens to this equation is t goes to infinity. What happens to this term? What's e to the minus infinity? 0. That goes away, so K2 is the voltage at t equal infinity, right? Do we have, what's the voltage at t equal infinity? 0, so it's 0, which is nice. That means Vc of t, the form of that will be equal to K1 e to the minus t over 0.2, right? The K2 is 0. Y'all agree with that, class? Now, how do I get K2? This is a class loaded with engineers. This is second nature. Well, what was the voltage just after this? Remember, I said the voltage can't change instantly, right? It's always continuous. It can't go from 0 to 1 volt instantly. So what is the voltage?
At 0.
4 volts. It's the voltage just before the switch transition, isn't it, class? Sure. So that means Vc of t equals 4 e to the minus t over 0.2. Now we've got the voltage across that capacitor for t greater than 0, don't we? Everybody? Now follow me on this. If we have the voltage for t greater than 0, we have this voltage right here for t greater than 0. This source is basically not even in the circuit. And I can do that, can't I, class? Y'all follow me? I just literally simplified that circuit for t equals t greater than 0. The question is, what is this current? What is this current going to be, anyway? Do we know the voltage across that current? Yes, right? That's Vc of t, right? It's time varying. You all see that? That's 4 e to the minus t over 0.2, right? If we divide that by the resistance, 3K, don't we have the current? How many see that? It really is this simple. There's nothing tricky about it. So I can say that therefore the current I want there is equal to Vc of t divided by the resistance, which in that case is 3K. And that equals Vc of t, or 4 over 3K e to the minus t over 0.2. Or that's 1.33 milliamps, isn't it, class? Times e to the minus t over 0.2 seconds. Now you can see that current decays down to 0 very quickly, doesn't it? How many see this? Huh? Y'all don't see it or not? What don't you see? Help me understand, because I don't know what you don't see. You don't know what you don't see? Gee, are you able to see that, what I put up here? All right, you understand how we got VC? You understand that or not? I'm sorry, I couldn't hear you. Do you understand how I got VC? How many understand how I got VC of T? What's that? If you do that, you're going to miss the whole point of this. This thing is trying to show you how to reason through a problem that will help you on that quiz. All right. Anybody that is distracted right now is a fool. I'm really trying to help you. You reason it out carefully. Go ahead.
Could you reiterate what K1 and K2 are?
Sure. K1 are arbitrary constants. Look at their place here. K1 is something that's the last thing you solve for because you don't know, right, what it is right off the bat. You know what K2 is. That's the voltage at T goes to infinity. Isn't it, class? Are you with me on that? Once you have that, then you can get K1 at T equals 0. You put in the voltage for, if K2 was not 0, then you would put in the voltage at T equals 0 here and solve for K1 because e to the 0 is 1, right? We did this, okay? Now, do the next problem. You can see how you're using everything you've learned before to do the analysis. That was a simple one. They get a little more complicated. A lot more complicated.
So your answer to the problem is 4 divided by 3K
Yeah.
e to the negative t?
They want current, right? Yes, sir. That was R Thevenin times C, right? R Thevenin, we figured was a parallel combination 2K times C was 100 microfarad, right? Y'all remember that? That's just straight up. We did that, right? Now remember, this stuff is so important. You see how you use the stuff from before because it everything's built on a prior step. If you don't stay up with it, then you absolutely crash and burn That's why I'm trying to encourage you as much as I can. Stay attuned to what I'm doing. Next thing, all right, I'm going to do, I want to jump a little. I'm going to do problem 327. A little more complexity, but it serves the purpose. Here, we're going to get much, there'll be one more. Okay. What they want is this voltage for t greater than 0, okay? Now that's the problem. That's the last thing you worry about. You all follow me? I've told you, and I'll keep saying this. The only thing we care about is finding the voltage across that capacitor for t greater than 0. Now you're going to use some of the steps you've learned before. This is Vc of t. I know the equation that governs that, right? Vc of t here is equal to some k1 e to the minus t over tau plus k2, right? And tau is equal to R Thevenin, the Thevenin equivalent resistance across the capacitor for t greater than 0. This would be for t greater than 0, as if the capacitor was a load, times the capacitance. Now we're going to go ahead and do this. Yes, sir.
Does the switch open or close?
It opens at t equals 0. I'm sorry.
Okay.
It could close, but we're going to do it open. All right? I want to be consistent. Now, if you follow me in this, you'll see how you can reason through these problems and they make perfect sense. There'll be a point where it's just so obvious. Like, how did I not see that? All right. For t less than 0, we get the voltage for t less than 0 first. Right? And the thing I told you to do was make it an open circuit and then redraw. Right? I mean, I'm just trying to get you familiar with this. So when I remove that, make it an open circuit, looks like I have 4 volts over here, correct? I still have 4 volts over here. Then I have 3 ohms here. Then here's my dangling capacitor. I'm going to make a point here about being attentive to detail. Then I got a resistor here. Then I got a resistor here. Forget the rest. And here is the voltage I want, right? Y'all agree with that, class? Now, think about it for a second. How many see just by inspection it's 4 volts? Without any math, you see that this 4-volt source is in parallel with those 2 points. How many see it now? It's that obvious. And people will, I'm telling you this from experience, they will find a way to make it complicated. Oh, I must use those. They're there. You don't need to. You reason this stuff out and have confidence in your reasoning. Don't ever, ever think it is not as simple as it looks. It is. Y'all follow me? This is one of the things that when I taught this one time during the COVID environment, I had so many people who just, oh, I must use this stuff. No, I made the problem so simple, but they would miss them. Because, oh, it can't be that simple. It is. Y'all see that, class? Without any further ado, you don't have to think any further than, let yourself trace it out. They're in parallel. We got that. So we have Vc for t less than 0, right, is equal to 4 volts. Do y'all agree with that? Now, in this one, this is a crazy. Okay. Now, next thing we're going to do is find the voltage for t greater than, as t goes to infinity. With me? I'm going to draw that circuit up. Please watch. So, now, come over here. I've got this voltage as 4. Next, I want to find VC as t goes to infinity. So, when the switch opens, maybe I'll go right here and talk my way through it. Take a look at this, class, and use your reasoning power. When this switch opens, you see how it literally disconnects this source from the circuit? How many see that right there? So that's a nicety. I'm going to do it this way. That's as disconnected as you can be. It's gone, right? Now, when I take a look at this, and this is the way I say, are there any voltage or current sources left in that circuit? What does the voltage have to go to? 0. There's a weighted discharge, it has to go to 0. So that, again, it's done, right? You can see how this parallels the last problem. Now when I do this, what happens? Now I need R Thevenin across this capacitor as if it was the load. I'll credit you with that, right, class? If you want to, I can erase it. It's 1 farad. I think I'll remember that. And if I look right here, take a look at this. What is R Thevenin between these 2 points? Don't say series again. What do you see here? How about these 2 in series? I'll give you that. You agree with that?
Yeah.
Sure, that's 6, right? In parallel with 3 is? 2. Amazing. Yeah. So that's 2 ohms, right? Therefore, we can find tau is equal to R Thevenin, or 2 times C, which is 1, or 2. Then we write the equation. It really is this simple. So the equation is VC of t is equal to K1 e to the minus t over tau plus K2, right? We know that the tau there is 2, so I'll put it in here. This is a little messy. I guess I'm a bit in a hurry. I'm sorry. K2. Right? Let's just talk about this. What do you know K2 is by this?
0.
How many see it's 0? Right? It has to be. So I just erase it. Now, take a look. By now, some of you are catching on. What is K1 gotta be? How many see it's 4? Because the initial condition is 4, right? You agree with me, class? So this is 4. Now I know this voltage, right? I know VC for t greater than 0. Please follow me on this. I know some of you really see it in our board, but some of you don't. Please be attentive. You all see we got the voltage across the capacitor, right? For t greater, that's the game. Once we have that, we see what they want. Oh, they want this voltage. Do you all see that this is in series with these 2? I mean, this voltage source has these 2 resistors in series. How many see that? Right? I can erase this one so you can see it better. It's the same voltage across those 2, right? We've got this voltage defined, don't we? So if we want that voltage, what is it? It's voltage division. Do you all see that, class? Simple voltage division. So that means if I want V out of t, it's just the initial value of the voltage times resistive division, 4 over 6, or 2/3. Do you all agree with that, class? How many see that right there? And that's it. If I wanted the current, the only thing I would do is take VC of t divided by 6, right? 6 ohms. You all see that? That's the way these problems always go. It's based on reasoning through what's going on. And please, please, don't look at all the solutions out there that have different ways of doing that will confuse you. Some will say we'll write a differential equation for that voltage and solve. You're going to just get yourself in a mess. And don't use Che. God, they'll mess you up with this one. I mean, I've had people get so fouled up, I don't know how to help them. But it says this here. Yes, sir.
So K2 goes to 0 because VC.
Well, say it again, sir.
K2 goes to 0 because BC, ST approaching 50 goes to 0.
That's right. If there are no sources, it has to be, doesn't it? Because let it decay down. This, I mean, I didn't, for this term, you see, for this term, as t goes to infinity, that goes away, you're left with K2. And if the voltage at t equal infinity is 0, that K2 is 0. Correct, class? Everybody? All right. Now, next, the final one. When I'm looking, I'll tell you what, I'll give you your quiz since you're so anxious about it and solemn. I'm gonna ask you to do this. Make sure there's one empty seat between you and your neighbors, so spread out. And I mean, I'll spread people out, so don't take offense. At least one, and move out as far as possible. Yes, sir?